So, welcome to today's event. I'm Gemma Monk-Hartley from Herefordshire Green Networks Building Sense. We're an initiative that was started in 2020 to bring together people, information and professional expertise to help with the challenge of making homes comfortable year-round in the face of high heating bills and, of course, cutting carbon emissions. Today, we're really delighted to be hosting not just one, but two experts on behalf of the Future Ready Homes programme, of which we, HGN, are project partners. And this is with support from the Green Register, who since 2000 have trained thousands of construction professionals from all disciplines of the industry to build better, more sustainable buildings. Just a tiny bit about Future Ready Homes, for those that you don't know, it's been running in Shropshire, Powys and Herefordshire since early 2022. It's been delivered by Marches Energy Agency and Severn Wye Energy Agency and being supported by groups such as ourselves in Herefordshire, Lightfoot in Powys and Zero Carbon Shropshire in Shropshire. The main focus of Future Ready Homes is to promote and support good practice energy retrofit of homes across the Marches area. And they're doing this through webinar series, why we're here today, retrofit advice, green doors, which some of you might have heard about, which concluded in October. And I'd just like to take this opportunity now to thank all of you that have provided feedback recently and in the past on our webinar series and your retrofit experiences. You have, lots of you have had emails from me asking for that feedback. It's really, really valuable to us, and particularly so right now because we're concluding Future Ready Homes 1. It's due to finish at the end of January, and we're applying for more funding to continue it for another 2 years. And your feedback really, really, really helps with those funding applications, and to make sure that when we do get the funding, which of course we're very hopeful we will, we can keep delivering what you need and helping you with your own retrofits. So thank you. Right, and finally, I'm going to introduce our webinar and our speakers. Like I said, we've got two today. We're going to start off with Julia Bennett, who is co-director of the Green, there she is, of the Green Register, and a low carbon architect with over 30 years experience. She trained as a passive house designer 10 years ago and works with both passive house and AECB building and retrofit standards. So we're in very, very good hands there. And Tom is our MVHR expert from the Green Building Register. He's got a background in architectural technology and is currently installing MVHR in his own retrofit, so is very familiar with the practical space constraints presented by these projects, and he can give us some real practical advice there. So yeah, today we're going to be talking all about building tight and ventilating right, why it's so important to have good air tightness, what that means, what that looks like, and how you balance it with ventilation to make sure that your homes are staying healthy, comfortable and functional. So on that, I'm going to stop sharing my screen and hand over to Julia.
Thank you very much, Gemma, and welcome everyone. Good afternoon. Thank you for joining us this afternoon. I'll just share my screen. Get some slides up. So I'm going to do a very brief introduction on airtightness. Let's just see if that will behave itself. There we are. And because airtightness isn't something that we've been designing for a very long time. It's an issue that we've all lived in very drafty, leaky houses. Most of us will have grown up in houses that you just had to put on lots of jumpers. Central heating came in after the war, and our comfort standards have gone up and up since then, so that we like to have our central heating. But what happens when you've got very leaky buildings is, of course, that the nice warm air that you're heating up in your homes is leaking out. So the importance of airtightness is actually the opposite of the air leakage that we already have in our buildings, and even modern buildings can be quite leaky. So the benefits of airtightness are obviously improved comfort. It reduces the heat loss. That is obviously a very topical issue at the moment with high energy bills. It protects the building fabric. So lots of old buildings will have moisture the risks of moisture damage within fabric build-ups, so within the walls, the roof, the ceilings, things like that. If we design our airtightness properly, then we can make sure that our buildings are in a much healthier condition. And also we can create conditions that are much better for healthy indoor air quality. So we've all seen some really tragic stories and pictures of properties where mold and condensation are causing problems, but we also have lots of modern materials inside our homes now that are making adding ingredients into the air mixture that are not necessarily good for us. So it helps. We can manage airtightness and ventilation together to make sure that we're going to have a healthier indoor environment. And let's face it, in the UK, we spend an awful lot of time indoors simply because of our climate, especially at this time of the year. So airtightness is a really integral issue for safe retrofit. And the reason for that is healthy buildings are a combination of reducing heat loss, sorting out the airtightness, and managing that moisture control. So these are the three things that link together to make better buildings. And there are hundreds of really good documents about retrofit, and two key documents that you might like to refer to that mention airtightness and ventilation are the Sustainable Traditional Buildings Alliance document. It's quite old now, but it's got some really accessible diagrams and tables in it, planning responsible retrofit, and then the Historic Environment Scotland Guide to Energy Retrofit of Traditional Buildings. And I bet Gemma and Tony and Jackie have got these documents in any resource list that they hold for you. So here's just a very simple diagram from that first document from the STBA, explaining why airtightness is a modern issue. So on the right-hand side, we've got that historic section of a building. We've got leaky windows, we've got gaps, very often suspended ground floors. We've got chimneys and very often lofts that you can see daylight through at the eaves and things like that. So that's where all your nice warm air is disappearing. And what we call that is unmanaged ventilation and unmanaged infiltration. So infiltration is the cold air coming in, and ventilation is obviously what we want to be able to manage to make sure we've got good indoor air quality, but it's not throwing all of our heat away. And so on the left-hand side, there are some of the areas in the picture that show how we can make sure that we've got less heat loss and greater comfort. This is another diagram that shows pretty much the same, and because I know that you'll either have the recording or the slides, you'll be able to look at this in more detail, but it's just worth noting just how many arrows there are there that are influencing how you treat your retrofit. So when we do retrofit, very often what we're talking about is making improvements to things like insulation and windows. And one of the most important things is well-fitted insulation. There's been some very good studies from the Passive House Trust. There was a document published last year, which shows that if you poorly install insulation, sometimes it can be almost as bad as if the insulation wasn't there because of the gaps around it and the air movement. So hand in hand with airtightness is very well-fitted insulation. And you can see in this picture that there are absolutely no gaps between those sections of insulation, and there's a nice oak beam showing just this is quite a historic property there. And then there's the phrase breathability. What do we mean by breathability? So breathability isn't really about whether we can breathe or not, or whether the building can breathe, because obviously buildings don't breathe. What we mean by that is the way that moisture can move through walls and floors and roofs. And we have different kinds of insulation and different kinds of construction materials. and some of them are open and they allow moisture to move, but they don't necessarily allow air, heated air to escape. And those are the kinds of products that we're looking for. Then we have materials that have closed construction, so they're very sealed. And since probably the 60s and since the 70s, when we had the oil crises, a lot of people did measures to their properties that tried to seal them up using especially materials with plastics, because they were becoming more and more prevalent. And we developed insulation materials that are called closed cell insulation materials. And they're the things like products like Kingspan and Celotex. Obviously, Kingspan is right on your doorstep in Herefordshire. And they have lots of issues, and they came up in the Grenfell Towers problems. But also from a point of view of retrofit, whilst they're very accessible and a lot of builders and retrofit installers like to use them, they do have some issues. You have to be very careful about how you install them. And that's where we talk about breathability. So we're trying to make sure that living in your houses, you're creating moisture just by breathing, by cooking, by bathing, by drying clothes, and the humidity goes into the fabric, depending where your airtightness barrier is. But we want to be able to make sure that it doesn't sit there, and it certainly doesn't get cold and condense inside the thickness of your wall or your floor or your roof, because that's when we start to have damage to your structure. So breathability is about moisture movement, and there is lots and lots of material about this now that explains how you can do this correctly as opposed to getting it wrong. And quite often when you're doing retrofit, you'll be taking out things that people have done in the past that they thought were improvements. So things like there were those wallpapers that I think you can still get them, that are like polystyrene wallpaper. And what they can do is, if your wall isn't dry, they can trap moisture in there and create mold. So I bet you've all seen some horror stories over time. So when we're talking about breathable construction, generally speaking, natural materials are moisture open, they're vapor open. And as I said, there's lots of guidance material, but here's just an image of a breathable improvement to a solid wall construction, where you've got lime render on the outside, lime plaster on the inside, and it's protecting it from the rain. But lime is not a closed material. It allows moisture to go through it, but it can be an air barrier. So it can be your airtightness layer. And this is the difference. Air and moisture travel through walls and floors and roofs in different ways. So when you put up a lime plaster, you're not necessarily preventing that moisture from going through. Whereas in the right-hand picture with modern materials, we've got things like impervious plaster on the inside and impervious render on the outside, and moisture coming up through the ground and creating conditions where that wall will never dry out, and it will hold that moisture. And if the conditions are not quite right, it will allow mold and condensation to occur. And when you've done cooking and bathing, and it hits the impervious plaster on the inside, if the surface is cold, again, the moisture will will condense. And I bet some of you have got condensation on your windows in the most recent mornings this week. And then when we're talking about airtightness, how on earth do we know how airtight a building is? And the general method of testing airtightness is with a calibrated door blower test. So this is what the kit looks like. There is another method that's coming through called pulse testing, which is now acceptable under the building regulations. But I'm going to explain this one because it goes hand in hand with another survey method to give you loads of information if you've got the resources to be able to do this testing. It's called pre-improvement testing before you start any renovation works. So this is a picture on the left-hand side of the front door of a property, and you can see the door on the left-hand side. So the door is open, and this kind of red, it's almost like tent material, is fitted tightly with expandable frames into the opening. And then the yellow circle at the bottom is a fan unit suspended within that. And what it can do is it can either suck air in or push air out, so that you can either pressurize or depressurize a property. And it doesn't mean you can't breathe when this is happening. You're perfectly safe when you're inside the property, but it creates a level of pressure with a calibrated machine, so that you can then take subsequent measurements of how the pressure in the house is decaying. If you've pressurized inside, so you can pressurize a house to the test value is usually 50 pascals. You might hear people saying 50 pascals. It's part of the description in the building regulations in Part L. And then you measure you take measurements over time, and it checks how much air is going out over time, so that you get a measurement of how leaky that property is. And every property that does an air tightness test is tested against 50 pascals, so that you can then benchmark it against other properties. And the one on the right is using a window. So where you haven't got access, or where you think there's a lot of leakage around a door, you can use a window instead. So that's a window, that's a smaller unit. And sometimes on very big buildings, you need more than one fan. So that's how you test, and you get a number. And the number is, when you're talking in passive house terms, it's slightly different than building regulations. But when you're talking in building regulations, it's the amount of air in a meter square that is passing through the fabric of the building, and the thickness is taken in terms of meter cubed, so it's a volume. And that's called air leakage. And so air tightness is the measure that we make to prevent air leakage. And I said it goes hand in hand very well with another testing method, survey method, and I bet you've all seen pictures like this, which is using infrared imaging. So infrared is measuring the surface temperature of what the camera can see. And it helps enormously with being able to see if you've heated up a property and you've also pressurized it during an air tightness test. So the air pressure is pushing the heat out of all the leaky bits in a property whilst you're in the middle of the air tightness test. And it therefore shows up where you've got problems. So you can see in this what this hasn't got is the temperature scale on the side of the picture. Normally you can't actually read one of these images without that. But you can see that one property has got a very red roof and lots of red bits around its door. And that probably means that the heating is on and the heat is escaping through the roof, and the door is not particularly, it's not come from the green building store, has it, Tom? It's not been installed to an airtight quality, and it's not insulated. And some of these cars look like they've only just been parked because their engines are still warm. So that's the sort of thing that can work very well, is to have airtightness and thermography together. Now, if you printed out this diagram on an A4 sheet of paper, this is a scale of the area of leakage. If you made all of the holes in the building into a drawing on a piece of paper, if you were doing a brand new building to passive house standard, it would be this little green circle at the top. But if you were trying to meet building regulations, the backstop at the moment, so that number for the passive house is 0.6. The building regulations backstop at the moment is 10. So you can already see the factor is completely different. Now the circles probably look quite small on your screen, but if you did print it out, you would see just how much air that is. I had my house, this very house, tested some years ago, and if you took all of the air leakage in the property, it came to the size of an A3 sheet of paper. So 2 pieces of A4 paper together, much bigger than any of that on the slide I'm showing you now. So, and this house is 17 years old. So modern construction is not necessarily any better than some of the older properties you might be talking about. And my house needs retrofitting, and I'll get round to it one day. Haven't quite started, but Tom has, so he'll tell you. And what can we do about airtightness? If you're not doing a whole house retrofit, and I think you've heard about that, then you've got small measures that you can do that you'll have heard about, and I bet Building Sense and Future Ready Homes have been telling you about these. So on the left-hand side is a picture of a sash window. Sash windows are, sash windows are absolutely notorious for rattling and being very drafty, but you can put draft stripping on them. And that comes into play for any openable windows or doors. And draft stripping has been shown with research with Historic Environment Scotland to be quite, it can be quite significant in reducing the amount of heat loss around windows that are not necessarily very tightly installed the way that we would do it now. And then if you're going to do something like internal wall insulation, then you would probably check the condition of the plaster. If there's plaster on the walls already, you might have to take some off. And in some cases for materials, you're asked to take any gypsum plaster off because that's one of the impermeable materials. But you would immediately increase the air tightness of a property by doing a thin coat, which is a leveling coat, straight onto a solid wall like brick or stone, and it's sometimes called a parge coat. And you would use lime plaster so that you're getting the breathable construction that we just talked about, but you're also improving the air tightness. Then whenever you're doing retrofit, one of the things, or any kind of construction, one of the sort of tenets is you might not be able to do it all, but even if you're only doing the windows or only doing the floor, try to do it to the absolute best quality that you possibly can. So for example, you don't want to be having to come back in and do it again at a later stage. So controversially, UPVC windows, you can get them triple glazed. You can do replacements. They're not to my taste, but some people don't mind the appearance of them. But you may well be retrofitting them again in 15 years' time because they don't necessarily last a long time. So if you can do better quality installations, then give that some consideration and maybe do phased retrofit rather than trying to do everything and spread your finances thinly. So other things that occur in traditional buildings are chimneys, and right at the beginning we had a diagram. It's quite, you can imagine, quite a lot of air goes, all your nice warm air goes shooting up the chimney. And these are chimney sheep or chimney balloons. These ones are sheep. They're made from sheep's wool, and you can't see the picture terribly clearly, but this is a fireplace. And just on the underside of the flue there, one of these chimney sheep has been installed. They're very simple. They're very cost effective. You can take them out again if you want to use the fire. So that immediately gives you a more airtight living room or wherever it is. And then just a couple of pictures more. Feel around any services. So lots of you'll have bits of plumbing and cabling coming through your walls and floors and roofs that are probably quite leaky. They're not fully finished. So you can make these much more airtight. This is the type of thing where you tape around and make sure that none of the air is going to get between the pipe and the wall. And some of you might be doing rewiring projects, and what this is showing is that If you're going to chase new wiring into the wall so that you keep the flush surface rather than having anything surface mounted, which can look quite unsightly. So you're cutting out sections within the wall for the supply cables coming down and for the switch socket outlets, the plug sockets. But this has got a paint on the back of it that is an airtightness paint, and you can either spray it or actually brush it on. And there are lots of different products now. This was called Purple Passive. It was one of the first ones. And what that means is that the gaps behind your sockets are not letting your warm air out. If you have an airtightness test, sockets is one of the things where you can feel with your hand the amount of air that is leaking out through sockets and plugs. So I'm going to stop there. There's probably questions for later, but I'm going to stop sharing. There we go. And hand over to Tom, who's going to talk about the importance of ventilation and a very specific kind of system called mechanical ventilation with heat recovery.
Julia, that was great.
Oh, bless you.
I'll just share my screen. Okay, so I'm Tom from Green Building Store. I'm going to discuss the ventilation aspect. Obviously, when building airtight, we need to then address the problem we've created, which is ventilation. I will also cover briefly a bit of airtightness, just to tell you what my experience was in doing my own and what I found. So firstly, what do we think about when we think about ventilation? A lot of people imagine a busy road full of cars with black smoke billowing out of the back. And a lot of people think if they live out in the countryside, then they're safe and we've got quite good air quality. But what you can have is a lot of people with log burners, a lot of farmers using chemicals, and obviously high levels of pollen, all of which you're exposed to when you're outside, and we're also trying to come into our home. And then we have indoor ventilation, which unfortunately very few people really consider as being an issue and a risk. Humidity, in terms of indoor ventilation, is becoming more widely talked about due to unfortunate news articles where we've seen children dying with mold-related illnesses. As the humidity in our air increases, so does the population of dust mite. I read a very good blog recently called My Life is Much Worse Now I Know About Dust Mite. It's not good reading. And then we've got volatile organic compounds, which are in most products that we use in our homes. So deodorants, cleaning products, paints, carpets, everything that goes into our home usually gives off volatile organic compounds, and the obvious one. So our indoor air quality can be up to 10 times worse than our outdoor air quality. And it's something that we very rarely think about. We always see our home as a safe haven from the pollutants outside, which is quite sad, really. And it can obviously have a big impact on our health when we're exposed to those levels of pollution. Some common things that most people use in their houses are cleaning products, deodorants, wet clothes drying on a radiator, which we all do. It's quick, it's easy. But what a lot of people don't do is open the window whilst they're doing that, because then we're letting the heat out. So when you've got a really high level of humidity in your house, so you should really open your window when you're drying washing on a radiator. Nice room odorizers, which are absolutely full of chemicals, and the innocent candle, which I imagine we've all got in our living rooms at this time of year, and people very rarely see it as something that's harming the air that you're breathing. You can get so-called green and so-called natural candles, but just because something's natural, it doesn't mean that it's good to burn it and breathe it in. So when we ventilate, we want to look at removing and diluting those pollutants and preventing those pollutants from coming into our home. So obviously, if you open a window to ventilate, you're letting the pollutants from outside come inside. In doing that, in solving those issues, we need to ensure that a ventilation system runs quietly, so it's not turned off, so you can have it on 24/7, 365 days a year. And it needs to provide an efficient solution to reducing heating demand. So let's say with natural ventilation, we're letting cold air in, we're opening a window, letting warm air out, cold air in. So we're losing a lot of our heat. And we need to help solve the unintended consequences of retrofit. By unintended consequences, I mean, if I make this window airtight, the unintended consequence is that it's going to get condensation on it. The room's going to have poor air quality. So it's about how we can avoid those issues. And the key one, it allows the introduction of an airtightness strategy. So this, for anyone who's familiar, is a screenshot from PHPP. And what it's doing is it's comparing building regs on the far left with Passive House on the far right. But what I think is more interesting are the middle columns. So let's take the far left column. We can see our heat losses. So we've got windows, we've got the ventilation heat loss, we've got the heat loss through the roof, through infiltration. And then on the second column along with the big orange bit is our heating system. And then below that, we've got internal gains. So that's things like people being in there, cooking, washing. And then below that, we've got the solar gain, so the sun shining through our window. So that is where our heating demand is coming from. As you can see, a large proportion of it is orange, which is our heating system. If you if you improve your air tightness to 3 air changes per hour, you reduce your heating load by half. You can see the size of the orange bar is reduced by about half. We've also introduced MVHR because we had to, because we've created an airtight building. But that just shows we've not improved the insulation. We don't improve the insulation until we get to the end, which is Passive House. All of the rest is simply improving the air tightness, and that has had a drastic impact on our heating load. So that's why I've kind of really focused on the air tightness in my own house over insulation, really. So how do we make our houses airtight? Well, this is my living room floor. This did go on for about 3 or 4 months, so I'm still working on rebuilding my relationship with my partner. But all the floorboards had to come up, so we couldn't use the room. You can see in the middle picture, on the far left picture, I then had to parge around the joists to create a nice level surface to which I could tape against, as you can see in the middle picture. So what I've got in the middle picture is an airtight membrane taped against the wall so that no air can come around it. And then I've got hemp insulation laid in between. The effect this has had on this living room is absolutely amazing. And I've been talking about airtightness for 10 years and promoting it. Only now I've seen the benefits for myself, and I've only done 1 room so far. So I'm looking forward to doing the rest of the house. And again, around the windows, it seems quite simple really when you think about it. Airtightness is simply just trying to stop as much air as you can from escaping. And these windows, the one downstairs, so on the left picture, that was a massive leak. You'd put a candle next to it and it would almost blow the candle out. So I've gone around there, I've parged, I've taped. I couldn't afford new windows, unfortunately. But again, I can now sit next to this window in a chair and be quite comfortable and not feel a draft on the back of my neck. So it really has massive improvement. So now we're getting airtight. We need ventilation, ideally mechanically, because I've spent all this money getting airtight. I don't now want to have to open a window to let fresh air in. Or I don't want to put a trickle vent in my nice windows that I've made airtight. So at around 5 air changes per hour, we start to need some kind of mechanical ventilation system. And at around 3 air changes per hour, MVHR starts to make financial sense. What I mean by that is that MVHR will always make sense in terms of giving you the best indoor air quality that you can get. By financial sense, I mean, it'll start recovering sufficient heat for you to notice a reduction in your heating bills. So what are the options, especially in retrofit where it's not as easy to fit in a full ducting system with an MVHR system? So we've got natural ventilation, which is trickle vents, extractors in bathrooms that come on when you turn the light on. We've got mechanical extract ventilation, decentralized and centralized. We're going to look at all these in more detail now. We've got PIV, positive input ventilation, and we've got MVHR. So in order of least effective to most effective, really, we're looking at. And we've got decentralized and centralized MVHR. Sorry, PIV should be just up there with natural ventilation. That's actually in the wrong place. So natural ventilation, we have trickle vents. What do we do when we feel a cold draft from a trickle vent? We close it. So now we've got no ventilation in our bedrooms and living rooms. On a windy day, on that side of the building, you've got great ventilation, providing you keep your trickle vent open. On a still day, you've got very poor ventilation because there's nothing to draw that air in from outside. We have intermittent bathroom extracts, which become clogged up with dust quite easily. They perform really well on paper, but the installed performance is usually very poor because we use flexible ducting to connect up to them. That's just kind of seems to be industry standard. And they're noisy, which is why we don't have them on all the time. We only have them on when we turn the bathroom light on, because we assume that is when the bathroom light's on, we assume we're having a shower, we're producing moisture, we need some extract in there. So that is kind of what we've all grown used to in terms of ventilation. So MEV, decentralized, what is it? So it's mechanical extract ventilation. It's similar to natural ventilation, except the extractors are very well designed, they're quiet, they're usually humidity controlled, so they're not running flat out all the time. We're running at a lower level and they increase depending on how much humidity they're detected. So that's the extractor that you'd have in your bathroom, and then you'd have a trickle vent in your bedroom. And the idea is, and the hope is, that we're extracting in the bathroom. That creates a negative pressure because it's sucking air out of the bathroom. So the air is then going to come in through the trickle vents in the bedroom. That is very unlikely to happen unless you're in an airtight building. Because if we're extracting in a bathroom, it's more likely that the air is going to come in around the leaky window or around a non-airtight suspended timber floor, for example. It's very unlikely that it's going to draw air in through the bedrooms. So the humidity controlled, good ventilations. I've had one of these. The product on the bottom is a Greenwood Unity extractor. It runs over time, very good quality, and it does what it should. It keeps the humidity levels in the bathroom down, but it's not dealing with the bedrooms. So there's no guarantee there of ventilation to those habitable spaces, which is what you want to be careful of, is when two people are shut in a room at night for 8 hours, they're not getting up and opening a door and mixing the air, they are still in bed. That's when you need ventilation. So then we move on to centralized MEV. So this is, instead of having a unit in every room through the wall to outside, you have a centralized unit, often in your loft, and it's ducted to every extract room. So your bathrooms, your kitchens, your toilets. Again, we've got trickle vents in the habitable rooms. And we've got an extract unit in the loft. So that bottom right-hand picture would be in your loft. We'd be ducting around the house. So we could use this semi-rigid ducting or a rigid ducting. And that'd then go to an air valve, like the bottom left, which would be in your ceiling. And that would be extracting the air. Again, the humidity controlled. So your trickle vent is also humidity controlled. So it's not just letting air blow in and out as it sees fit, depending on the weather conditions outside. It's got a clever membrane in it that opens up when it detects humidity, so it lets more air in. Your extraction unit is also humidity sensitive, so that will extract more air when it's more humid. But again, there's no guarantee of ventilation to habitable rooms, because there's no mechanical system in that habitable room blowing air into it. There's nothing, it's just a trickle vent that's humidity controlled. We've then got PIV, positive input ventilation, which you have to be very careful of. I'd never really recommend it, just because the risks far outweigh the benefits. What this does is it sits up in your loft. It brings air in from the loft and it blows it into the house. And people's feedback on using this is usually very positive. It does get rid of that humidity. The problem is where it's putting that humidity. It's often putting it into the building fabric, into hidden places where you can't see, such as your suspended floor void, or such as a cavity around a leaky window. It's moving the problem to somewhere where you can't see it. In theory, it should go out of trickle vents, but it won't necessarily do that. It'll go out of the easiest place that it can find, the lowest pressure run. The air in the loft can be very humid, especially at this time of year. I get so many people, friends and family, saying my loft is dripping with condensation. Why is that? It's because air is getting up through the gaps around the loft hatch from the house, the warm, moist air, and it's condensing in the loft. So you've got a very humid loft. This is then blowing air from the loft into the habitable rooms and into your house. So sometimes at some points in the year, it'll be good because there's dry air in your attic, in your loft. But especially in winter, it will be quite humid up there. Decentralized MVHR. I've seen a few questions about this pop up in the chat. The benefits of it: you don't need a ducted system. It's one unit per space. So you can see here in this living room, it's this unit, this white unit sat on the wall. It's quite big. The good ones will be quite big because they're trying to recover heat. We need a heat exchanger. We need to be insulated. Some of them can be ducted to a second room. So there's a product here on the bottom left. This is called a Blue Martin Free Air. And it sits in the wall. So it's supplying air out of the bottom of it. It supplies fresh air. And then in the top of it, it's extracting stale air, in theory. And it can be ducted. So you could take a semi-rigid duct or a rigid duct from the bottom of that to another extract room, or such as a bathroom or a kitchen. And you can also take another supply duct, for example, to a bedroom. So I really like that product, especially for small apartments or small garden rooms, things like that. The problem with these is that there's a mechanical fan in every room. So if you've got one of these in a bedroom, they can be noisy. Manufacturers will tell you that they're quiet. That's probably on a very low airflow rate. So whereas when there's two people in bed, you want quite a good airflow rate. They might be around 50 to 60 decibels. So that is really quite a noise to have in your bedroom. 25 decibels, for example, is inaudible. Centralized MVHR. So this is kind of seen as the optimal solution to indoor ventilation, especially it's used a lot more and more in new builds, and it is likely to go into building regs at some point. It is doing in Scotland from next year, I think. So we've got a central unit, which in this picture is shown in the ground floor utility room. And we have a ducted system to the extract rooms. And we have another ducted system to the supply rooms. So every bathroom, kitchen, utility room is having the air sucked out of it continuously. And every habitable room, bedrooms, living rooms, studies, golf swing rooms in some houses, They're all having fresh air supplied to them continuously. When we extract the air, we're extracting warm, moist air. That comes back to the heat exchanger in the MVHR unit. We bring fresh air in from outside, and that recovers the heat from the outgoing air. So a good unit will recover up to about 93% of the heat that is extracted. So ventilation heat losses drop to almost none. So we're pre-warming that air that's coming in from outside. It acts as the lungs of the building, which removes the need for any other ventilation. So often people will say, that's great, so do I still need my extractors in my bathrooms? No, you don't. You don't need any other extractor. You want to let the ventilation system do everything, and that way it'll recover as much heat as it possibly can from the outgoing air. So what are the benefits? Health, we're removing and diluting those internal pollutants down to a safe level. We're reducing condensation, so the ideal threshold for humidity for us as humans is between 40 and 60%. And you can see that's a bit of a sweet spot. So anything wetter, we see an increase in dust mites, fungi, bacteria, chemical interactions, and then dry air can also be a problem. So I've got quite dry air in this room, which is why I keep having to drink my water. I've got a ventilation system in here running in a meeting room, and it's running a bit too high for one person. So you start to see irritable sinuses, dry throats, dry eyes, and again, an increase in viruses and bacteria. In turn, that helps prevent mouldy and damp conditions. So the reason we have mould around our windows is because the window reveals are typically cold, because it's just tends to be plasterboard straight onto the masonry. So the air, the warm, moist air in our room gets to that cold reveal. It cools down, losing its capacity to hold the moisture, and it condenses, which then sits there and turns into mould. And if we keep the humidity down, we're reducing the risk of respiratory illnesses, infections, and allergies. And there's another dust mite. Now my arch enemy since I read that blog. Comfort, which is a huge one for me. What I found is comfort above everything else that I've found so far with my own retrofit. I am so much more comfortable in that house. We're eliminating drafts from open windows and trickle vents and leaky, poorly installed windows. We're encouraging even temperatures throughout the building by keeping a continuous circulation of air. And it's controlled ventilation. So if there's one person in the house, you can turn the ventilation down. If you're having a party, you can turn the ventilation system up. If you're cooking and producing a lot of moisture, again, you can turn the ventilation system up. We're reducing outdoor noise pollution because you've got no trickle vents letting noise in. You don't have to open your window and put up with traffic noise. And again, we're allowing an introduction of an airtight building fabric, which I did used to have in the efficiency section, but I've now moved it to comfort because it has had a huge impact on comfort. And then efficiency, so we're recovering up to 93% of the air that we're extracting. So ventilation heat losses are minimal. A low pressure ducting system creates an efficient solution. So this system should be cheap to run. It should be £40 to £60 a year to run electrically. And again, it allows the introduction of an airtight building fabric. So just to summarise, it's optimal ventilation levels. It's very energy efficient. We're recovering the heat rather than bringing it in at outdoor temperature. We're making sure that we've got the correct air flow rates to and from each space depending on the uses. And we've got a continuous circulation of air. We're providing clean, fresh air rather than recirculating the spent air. So the air is filtered. The supply air is pre-filtered, so you're removing pollen, you're removing any kind of airborne dust or particulates, and you're supplying completely fresh air. That does all depend heavily on good design. There's some shocking systems out there, which you do all need to be very wary of. And system design, I would say, is the most crucial element. That picture on the right, you've got a good quality, affordable MVHR unit. The ducting system that it's connected up to, as you can see, is shocking. It's tumble dryer hose, flexible ducting. There's no silencers on there. There's been no consideration given to that ducting design. So the first thing we look at is pressure loss. So when explaining pressure loss, I always say imagine a straw. A small straw that's bent is quite hard to blow down or to suck up. With a big straight straw, it's much easier to blow down or much easier to suck up. It's the same with a ducting system. The ducts need to be very carefully sized in accordance with the air that they're trying to carry. If we keep the velocity in the duct down, we're preventing noise that's coming out of the air valve in the room. So we don't want our air to be rushing around a ducting system at 6 meters per second. By the time it's coming out of the air valve in the room, it should be at about 1 meter per second. Specification of the duct is key. Some of they need to be smooth internally. Some of the cheaper ones are corrugated, or for example, flexible ducting can crush down and air is going to struggle to flow through there. It needs to be as smooth as possible. And every bend on the system increases pressure loss, the resistance to the air flowing through it. That doesn't mean that we should remove bends from systems. We have to have them, but it just needs to be considered at design stage. Sound is a huge one, and a lot of people have to turn their systems off because they're too noisy, which just shouldn't be a compromise you have to make. It can be made silent through good design. So if you have a designer and they know you want a quiet system, you'll have silencers on your system to make sure that you're not going to hear it. And you should be able to ask for design data for sound data at design stage. So the designer should be able to say, yes, your system is inaudible. Or no, it's not inaudible, but it can be. We'll put a bigger silencer on it. And you want it to be less than 25 decibels in habitable rooms and less than 35 in extract rooms. So you won't hear 25 decibels. 35 you wouldn't hear in a kitchen above the sound of a fridge freezer, which is typically 45 decibels. Good MVHR units aren't small because we've got a big heat exchanger and a lot of insulation in them. So you can see this Zender one, for example, on the far left. This will do anything 100 up to 400 meters squared. Same depth as a kitchen unit. It's about the size of a washing machine. So you need to allow space for this early on in your project. Retrofit, obviously, can be tricky fitting ducting in. What you've got on the far left is you've got a ceiling mounted MVHR unit above what's going to be a toilet room in this old Victorian building. This client understood that compromises did have to be made. For example, here they're going to have a lowered ceiling, which, as you can see up there with the MVHR unit, they've lost some of their nice detailed coving along the ceiling and wall junction, which is a small sacrifice they had to make. Fortunately, we didn't have to do that in every room. It was just this room. Often in retrofit, as you can see in the middle picture, it's easier to put the unit in the loft, so long as it is a warm space. It can't be a cold loft space, because then you get problems with condensation and heat loss. So if we put a unit in a loft, in a retrofit, we can usually get all around the roof space and drop down to every room below. We're not having to contend with solid floor joists. You don't need ceiling voids. Minimal boxing required. So that can be a nice option. As you can see on the picture on the far right, we've got ducting running in the eave space in the loft. There is insulation there running below that ducting. That's in the process of being removed. There should be no insulation below that ducting because it needs to be within the thermal envelope. Flexible isn't an option. The pictures speak for themselves. The connections aren't airtight. We've used cable ties to connect some of that ducting into place. Air is going to struggle to flow through those ducts nicely, and it rips very easily. As you can see on the picture on the far right, that ducting has got a tear in it. So air is just escaping from that into the ceiling void above. So the typical options are rigid steel or semi-rigid plastic. You need to consider your joists, your plant space. People often think semi-rigid systems save a lot of space. That's not always the case. as you can see on the picture on the right, there's a lot of ducting going back to that MVHR unit, because some rooms need 2 ducts, some might even need 3 ducts because they're carrying a lot of air. Whereas with a rigid system, only 1 duct is required. Joist specification. What size ducting can we fit through your joists? That might determine whether it's a rigid or a semi-rigid system. Do you want it exposed or hidden? If you want it exposed, so it's on show, you want to go with steel. You don't really want the plastic semi-rigid stuff on show. People often ask which ones are better, and the advice you'll get will vary drastically depending on who you go to. A lot of people manufacture their own semi-rigid ducting, so they'll obviously say semi-rigid is the best. The truth is, and speaking as an independent person, both systems will perform as well as each other, providing that the design is done. That is the key. They have to be designed. It's not an off-the-shelf product. So here's some pictures. For example, we've got an exposed rigid ducting system. We've got some semi-rigid ducts on the left, nicely installed in a roof space. We've got semi-rigid ducts going through the posin metal web joists. And then on the right, we've got a rigid duct going through a timber eye joist. Those semi-rigid ducts on the left wouldn't have gone through this timber eye joist because there's too many of them. And when you cut the holes in those timber eye joists, they have to be at certain centres. So in some cases, semi-rigid won't work and rigid will. In other cases, rigid won't work and semi-rigid will. So there's not one answer. Every house is different. The control of the system should be really simple, is our belief. Everyone should be able to use them. There's typically 3 fan speeds. There's fan speed 1, which is holiday or away, for obviously when you go away. It drops the ventilation rate down. Fan speed 2 would typically be standard operation. So when there's the standard, if you've told us this house is a family of 5, we'll design fan speed 2 to provide enough air for a family of 5. And fan speed 3, which is a boost, the Germans call it the party button. It's for when there's more people in the house or when you're cooking or showering. And there's unoccupied for when the house is empty. The unit should never be turned off because it does contain moisture in the ducting system, in the heat exchanger, in the filters. If you turn it off for more than, say, 10 days, you will start to see some mold growth in there. Every mechanical system needs commissioning. Someone with experience should come out and commission your system and sign it off, especially with MVHR. It's a sign off for building regulations part F. It's required. And it's a good option for the person commissioning to do a really detailed handover to the end user and say, this is what your system's doing, this is how to use it, this is how to keep on top of the maintenance. And it certainly shouldn't be performance-based commissioning. So by that I mean someone goes out to commission a system, they get the airflows that it's designed to, but it's too noisy, so they turn it down, which is a compromise. You're saying, yeah, you can have a quiet system, but you can't have the airflows you need. There should be no compromise. There doesn't need to be. There's the knowledge and products out there to provide an inaudible, high-performing system where you're getting the airflows that you need. Should be no compromise. If someone turns up with one of these to commission an MVHR system, they should really be using a proper anemometer or bolometer to get a true airflow reading. The picture with the red cross through it is only really suitable for traditional ventilation extracts. So in summary, ventilation is essential, especially when introducing an airtight strategy, which I'd recommend to anyone considering a retrofit. The ventilation method very much depends on the building and the proposed level of work. I'm not doing a deep retrofit, I'm doing room by room, but I am having to get my ventilation system in first because in my living room at the moment, I've got condensation all over the windows because it's airtight and I've not put my MVHR in yet. So you can do it cleverly. It just needs good design from someone experienced. And whichever system you use, carefully consider it, get expert advice. Don't just get an off-the-shelf product. Thank you.
Lovely. Thanks, Tom. That was brilliant. sorry guys, we've had quite a long session there and you have got questions, so we'll be hopping straight onto those. But yeah, that was really, really interesting. Sorry about that unintended consequence that you've experienced, Tom. Couples cancer. Or
given my job role as well, you wouldn't think that would have happened, but it has.
No, there you go. So we can't be held responsible for that, everyone, and take that into account when you're planning your retrofits. They can be quite involved, but well, they are involved. But obviously, we've been talking extensively here about the health, comfort, and energy performance that you get as a result. So yeah, right. Let's go over to Tony and over to the questions and see what we can get through in the next 25 minutes.
Yes, my thanks. Loads and loads of amazing content there. Jem, can you turn my video on, please?
I think so.
I'm assuming people want to be able to see me. I may be wrong. Right, I think this is one for you, Tom, slightly off topic. Sorry to start off topic. Is it true that some air conditioning units are air-to-air heat pumps?
That is true.
Right. Okay, that's a useful answer. Lou was asking a question, general HGN question. Is there a similar organisation to HGN in Worcestershire? Can someone pick that up, Jem?
I will pick that up. But I think the answer is no. We tend to cover Worcestershire as well. So in terms of information, if there is a similar future ready homes type thing in Worcestershire, again, not I'm aware of, but I will have a look and see if I can let you guys know.
Okay, thank you very much. A question from Carol. These modern adaptations in airtightness, are you finding this may cause more damp and mold related issues? Carol, I hope that's been answered during the course of the presentation. This is very much the point. The insulating and sealing up airtight buildings means, of course, that ventilation is absolutely crucial to prevent damp and mold issues. Right. And a question from Helen about Julia, I think this is going back to you at airtightness. Old timber sash windows she has in her property where she has secondary glazing, which she thought worked very well. Why is it being derided? I'm not sure it is derided. I think we're quite fans of secondary glazing. Sometimes it's the only option in a listed building, and it can perform, I think, almost as well as double glazing.
Yeah, where you've got very heritage sensitive listed buildings, then very often you're not allowed to replace the windows or make any upgrades on them. But I think secondary glazing has a bad name because, again, in the 70s and 80s, they tended to be not very beautiful. And let's say there are many more products on the market now. You can get ones that have got a bit of a heritage character to them. You can get ones that are magnetic strips so that they're magnetic fixing, so they're easy to take down. You can get ones that open out like an internal casement. So I think the market has got so much better, and certainly conservation officers are coming round to it a lot more readily these days.
Yeah. Thank you. Okay, it struck me, if you want to test, obviously, how well your secondary glazing is performing, then an airtightness test might be just the ticket. So you'll actually know rather than just assuming that it's performing well. In terms of the scores you went through, Julia, I wondered if you could help me to understand. Passive House 0.6, Enefit is 1, and so on and so forth. I think you had two different measures. ACH, I was thinking that must be air changes per hour.
It is. So when you're doing anything that is using Passive House methodology, and Tom mentioned a calculation tool called PHPP, which is the Passive House planning package, we're generally talking about air changes per hour. So that's the whole volume of the property and how many air changes per hour. And when we're talking about Passive House certification, the 0.6 relates to that, air changes per hour. So in effect, 0.60% of the, 0.6 of the volume of the house is being changed per hour. When we're talking about building regulations, we're talking about meters cubed of air, so an equivalent of the amount of air that is moving through 1 meter square of wall or floor or roof per hour. So it's much more about the actual fabric elements and the air passing through that, rather than the whole building as a measure. Does that make sense, Tony? Does that help you understand it?
I'd like to say yes. So the building regulation specification now for new builds is 5. So it's not 5 air changes per hour. It's 5.
It's 5 meters cubed of air passing through 1 meter squared of fabric. Fabric means an element of the house, so a wall or a floor or a roof. And I think I've actually said the wrong terminology. So building regs is talking about air permeability. So if you think about how permeable that 1 meter square of fabric is, it's how much of your nice warm air is passing through that per hour. And if you think 10 meters cubed sounds like an awful lot, that's because it is passing through 1 meter square of your wall or roof or floor per hour.
Yeah. Gotcha. Okay. Thank you. A more practical question about products, which we've had a couple. I see you picked them up in the chat. Thank you. But just to share, where we're talking about sort of drainage and services, these little holes in the house, what sort of products? I mean, the builders love the old expanding foam because it's very quick and easy and cheap. What can we fill up our holes with to improve air tightness that everyone can do?
So the expanding foam will eventually shrink and decay and go brittle, and things like duct tape are just not airtight. They don't have the adhesion to last the tests of time, and the little bits of movement that you get between different parts of a building. So we do need to use specialist products, but if we're really careful about how we use them, we can. They're expensive. They're much more expensive than expanding foam and duct tape, but you will not get the result using expanding foam and duct tape, but you can be very careful to make sure that you're only using a small amount of the specialist products. So for example, if you've got something like a 4-inch pipe going through a wall at the back of a toilet, very often that's a place where you get lots of air leakage. And if the hole is huge, you know, the gap around it, what you can do is you can use the expanding foam as a base, and you can let it set and then cut it with a craft knife or a Stanley knife to make a base, so that when you apply the tape, the very specialist air tightness tape, you've got something hard to press up against. So you make the connection around to the wall and to the pipe, and you're just using the foam, the hardened foam, as a temporary support, but the actual air tightness is being created by the tape. Yeah. And it's tested to last for decades. You know, it's you know, the reason they're expensive is because they really do the job, and they do it for a very long time, so that you can be confident you're going to get the results you want. But you have to make sure that the tapes are very well pressed down and very connected to each other, where you've had to use several pieces. When you're doing new build work, you can get things called grommets, which are squares of a material called EPDM, which if I had a brain at all, I'd be able to tell you what it was, but it's like a plastic material, impermeable material, with a kind of a star-shaped cut in the middle, and you can sleeve it, you can put it onto a section of pipe and then tape around it against a wall, and that gives you an airtight seal. But usually in retrofit, we don't have the luxury of being able to take pipes apart to get the grommets on. Okay, that's a good tip. Thank you very much. We've got one from Dan here. He sounds like he's having a little bit of a shocker with kingspan between the rafters. Not an uncommon situation, this, when a junior labourer or someone has been cutting the kingspan and it doesn't fit tightly between the rafters. Do you have to completely remove the ceiling and replace, or can you inject some insulation into the roof void to fill the gaps if the panels of kingspan don't fit?
properly?
Goodness me. Yes, I think someone did comment in the chat. It is almost as if the insulation isn't there, and this new research on what's called thermal bypass, which is the movement around the insulation, making it almost useless. You have to find a way to. I don't think you could confidently blow in something like cellulose or beads to resolve that situation. Ideally, you would either take all of the Celotex or Kingspan out and put it in with a more soft, something like a flex fit wood fiber material, which is a semi-rigid, and it snuggles in between the rafters so that you don't get any gaps. Or you could leave the boards in place and very carefully kind of stuff the gaps with mineral wool or sheep's wool, and perhaps add an extra layer underboarding the rafters, so making sure that there's a layer of insulation that goes underneath the whole of the rafters so that you're not getting air leakage around. But that's a tricky one. I think you would, if it was me, I would take the ceiling down just to be able to do a good job, which of course is a major undertaking compared to drilling a few holes and pumping something in. But I don't think you'd get a confident result doing it any other way.
Yeah, Dan, we feel your pain. Tom, quick question for you, just to share with everybody, since we're talking about materials, why did you go for hemp to insulate under your living room floor? Shall I read out your reply?
You can do, yeah.
Go on.
Yeah, it was mainly, well, hemp is really good with moisture, for moisture wicking. It was also a decision based on me wanting to do the best for the environment. It was also based on I was at the start of my retrofit and was feeling confident about my budget. I'm now back to cheaper products. But yeah, it's lovely stuff to work with, so I'd recommend it.
Right, sticking with money then, inevitably we've been asked about costs. Very difficult for you. Can you give us some sort of ballpark ideas of a cost of an MVHR system installed, and indeed the cost effectiveness of MVHR?
Yeah, so let's take a typical UK house, maybe larger, so 100 meters squared, 3-4 bedrooms, maybe about £6,000 for a good one. That's not installed. Another maybe £3,000 installed.
Okay.
Cost
That's
effectiveness. People often ask what the payback period is with MVHR. I'd always say there isn't one. The payback period that you get with MVHR is the fact that you've made your building airtight. That's where your payback period's coming from. So you need less heating in the first place because you've got an airtight building. If you were trying to save costs on energy bills, MVHR isn't the way to go about it. I'd suggest solar or air source heat pump, but certainly an airtight building fabric.
Okay, let's get on to some practical questions. Jen was asking, her property, she's got very thick walls, 600 mil plus. How does that work for MVHR? Presumably you need a big drill to get through it.
Yeah, nice big core drill. Yeah, it's fine. We put MVHR in all kinds of buildings like that. The design principles would all remain the same. Obviously going through walls will be a challenge. So worth having a good diamond core bit. Okay,
so similar question. What are the issues with fitting MVHR in a listed building?
Well, yeah, it very much depends on each building. Some don't like to have lowered ceiling voids. We're not allowed. You might struggle to get the external grills on the wall in a place that's allowed. So we've never had one we couldn't do, but you have to very much take it on a case-by-case basis and try and hide everything away.
Right, okay. I should say, actually, can we have some costs for the other systems you recommended, the DMEV and the PIR, for instance? Can you manage that off the top of your head?
PIR is about 350 quid. PIV, sorry, is about 350 quid, which is why a lot of people go for it, but do be very careful. I really wouldn't recommend it. Centralized MEV system from a company such as Airtight, who do a good system, might be a couple of grand, 2 to 3 grand. If you want, what I'd always suggest is that if you want to go home and improve your ventilation now, and you've got intermittent extractors in your bathroom that come on when you turn the light on, buy the Greenwood Unity extractor, which is moisture sensitive, and simply replace them all in your house. You've immediately improved your ventilation. They run all the time and be humidity sensitive.
Right. Could you give us a little more detail about that? That sounds terrific.
Yeah, so it's just a product that sits in the ceiling or wall. It can be replaced. It can replace the one that's already there. It runs all the time at a very low level. If you start showering, it'll detect the humidity. It'll increase its extract rate to help clear the air, and it's nice and quiet. So it's a win all round, and it's not too expensive. Does need installing by an electrician, unless you're good with electrics.
So what sort of cost is the unit? Do you know?
About £80 per unit.
Great stuff. Thank you. Yes, right. Wood burner. How does the wood burner work with MVHR? Obviously, a wood burner needs a good supply of air to keep it going. How does that work?
So it'd have to be a balanced flue system. So it'd have its own air supply from outside via a small pipe into the back or the underside of the burner. And that's where it'd take its air from.
Okay. I had a general question. Have you got any comments on dehumidifiers? I suppose you've just made one on the by recommending the Greenwood system.
Yeah, I'm assuming let's talk about dehumidifiers in the general sense. So a box that you plug in and it collects the water. They're good. They obviously need emptying. They're good for drying, washing. They're better than nothing. They're noisy. But yeah, it's certainly better than doing nothing. I've got one in my house running at the moment.
Okay, thank you. Similar question, interesting point. When it's this sort of weather in the winter and there's a lot of humidity outside, how does the MVHR deal with not bringing moist air into the house? I suspect there's some sort of filtration going on.
Well, so on a day like this, it is moist outside, but it's also quite cold. So the humidity outside is very high because the air is cold. As we bring air into the building and it warms up, its humidity drops because it's warming up, so it's got more water-bearing capacity. There'll also be some condensation taking place in the heat exchange process, so some of it may well be drained away. So we're supplying air at around 40 to 60% relative humidity.
Right, so the MVHR unit is set up to deliver what is needed.
Yeah, and it will condense. Like I say, cold air. Let's say if you've got cold air at 100% relative humidity, that's basically mist. If you then warm that air up, it's going to drop to say 50% relative humidity because it can hold a lot more air because it's a lot more moisture because it's warmer. As soon as that air cools, the humidity of the air increases because it can't hold the moisture anymore.
Okay. Question about ducting, quite technical here from Anna. Which type of rigid ducting has the least impact in terms of carbon footprint in manufacture? Do you know?
That's a very good question. I don't know. I'll know people who do, so I can certainly look into that. With the rigid ducting, we use the Lindab system, which is manufactured in Leeds. We're in Huddersfield. Obviously, where they get their steel from will have a big impact on that.
Right. A quick question from me, actually. Where do you put the MVHR system? Where do you put the unit in the house? Comment from Ian. Remember, you need access to change the filters periodically. I know often the loft, I think, is the most convenient place to put it, but as you're getting a bit older and you need to get at it to change the filters, you might not want to keep going up and down the loft ladder.
Completely, yeah. Especially if it's a new build, I'd always say a ground floor utility or plant room that's easily accessible.
Yeah.
If it's a retrofit, again, still ideally ground floor or somewhere accessible. However, the duct runs can often be quite complex with retrofit, so it's worth thinking about how you're going to get your ducting around the building before you decide on where to put the MVHR unit.
Right, sorry, I'm trying to read and listen at the same time. Back to wood burners, ventilation for fireplaces, wood burners with underfloor void with air bricks below as wooden suspended floor that is insulated as Tom showed. What is the best solution for this?
Yeah, so again, if you're making your floor airtight, you're eradicating your air bricks, so you'd need a balanced flue system again. So your log burner would need its own air supply. Fireplaces are a bit of a different matter. We'd always say you're going to have to get rid of your fireplace. If you can't get rid of your fireplace, you just have to turn the MVHR off whilst you have a fire.
Okay. Should make a comment. Actually, we did have a talk back in the summer about air quality and wood burners, and we were all rather surprised at the particulates and how bad for your health they are. Mike is making a comment. As a retired doctor with an active interest in air pollution, I'd strongly suggest removing all wood burners. They are a source of air pollution, a third inside the house, 2/3 to your neighbours, and lots of health implications. So, yeah, something to bear in mind. Julia, can you pick this one up? Which thermograph was used in Julia Bennett's piece? Do you know?
Can we explain the question a little bit more? It's just something called iPhone, but is iPhone still with us?
Okay, we'll come back to that.
Yeah.
Julia, you mentioned 2 information sources at the start. Can these be spelled out, please? I should say the slides and the recording will be available in the usual way, so you'll be able to look for those. Yeah. Jem, I'm sure we can put that on an email to everybody.
Yeah, I can send links to those reports as well that Julia referenced.
It was the well, they were both about planning and designing a responsible retrofit of traditional buildings. One of them was produced by the STBA and one by Historic Scotland. I hope that's helpful.
I can put the links in the chat if it's helpful.
Okay, that would be great. What are the views on using the aero barrier process or technique to achieve air tightness in retrofit? Any views on that, either of you?
I'm not familiar.
Not familiar.
Bob, do you want to tell us a bit more about it?
Yes, it's an acrylic vapor system, which is applied obviously with an empty house, and the acrylic vapor apparently condenses into the points where the leakage is taking place.
Oh,
and you have at the same time you have the airtightness testing equipment in place. And you use this vapor to condense into the holes until you achieve, the parameters you're after.
Okay. So my first thing is that acrylic sounds moisture closed. So you're creating something that is not going to be able to respond to moisture. So it depends what you've got on the outside as to whether the moisture in walls and floors and things is going to be able to dry out over time. And I think for me, I'm a fan of natural materials. So for me personally, I wouldn't use a plastic-based material if I could help it. And the third thing would be that buildings do move. So how I don't know the system at all, but you would have to make sure that you had enough adaptability within the system so that if the building's moving through window frames, heating up in the sun, and the timber or whatever the material is moving differently than the solid wall or whatever. So those are 3 things that come to mind, but I'm not familiar. So I maintain an open mind, Bob.
That's a good effort. Thank you very much, Julia.
If I can find a link, perhaps I'll post it.
Thank you.
Okay, thanks. We're just about running out of time. Very interesting question though from Sue, which I just wanted to bring up about MVHR. How does MVHR cope on a very hot day? We had a talk in the summer that we did about keeping cool in a warming climate. You might want to look back at that, about shading is more and more of an issue, will become more and more of an issue with climate change. So we're talking about heat recovery. How do we cool down using our MVHR?
Yeah, so I'd say MVHR won't cool down, and certainly to look at the building fabric instead, such as shading. You can get cooling units for MVHR. It's kind of passive cooling, so it won't do anything like air conditioning would. It'll just slow down the rate of overheating. But what your MVHR system will do on a hot day is it'll say, right, it's getting hot in here, it's getting above comfort level, it's 22 degrees now. What temperature is it outside? Oh, it's 19 degrees. All right, I'll stop recovering heat. I'll start expelling this air, and I'll start bringing air in at external temperature. So I'll start bringing it in at 19 degrees instead of recovering this 22 degrees. And that helps slow down the rate of overheating. And for that reason, it's good to consider where you're putting your intake grill on the outside of your building. If you can get it on a shaded elevation or a north elevation, that's very effective for your summer bypass. But yeah, it'll stop recovering the heat. It'll recognise that. If you've got air conditioning with the MVHR, which some people do have, then your MVHR will recognise that, and it'll say, right, it's 17 degrees inside. I'm going to recover that cool to help reduce the requirement on the air conditioning. So it's quite intelligent.
Wonderful stuff. Right, we really are short of time now, and we've just about run out of questions. Lots of thanks coming in, of course. So thanks to Tom, and thanks to Julia. I'll hand it back to Jem for proper wrap up.
Yes, I'll make it very speedy because we've had an hour and a half. So thanks to you both. That was really, really useful. For the rest of you who's still here, we've got one more webinar coming up before the end of the year. That is for next Monday, the 11th of December. And that is all about what's going on above your head. So insulating roofs, lofts, ceilings, sloping ceilings, and such like, really tricky areas, but really important areas if you're going down the insulation route instead of, or as well as, the airtightness route. So come along for that next Monday, and then there'll be another one coming up in January. As usual, expect to see an email from me with a recording of this on, and some of the links, what we've been speaking about. And look out for that invite for next week, and for the request for some feedback. It would be much appreciated. So yeah, that is us. Thank you, everyone. Tom and Julia, do you want to stick around just for 5 minutes? But everyone else, see you next week, hopefully, or if we don't, happy Christmas. Have a lovely Christmas and New Year.